One of the famous quotes is, time is defined to make motion look simple.
Okay.
Because you cannot describe motion without some reference to time.
Right.
And so you define it so that motion is something we can describe easily with equations and things. So that's kind of a cop-out answer, but it's a very functional answer for the physicist.
Yeah.
I also think of time as this prison. Time makes us all a prisoner of the present, forever transitioning from our own past into an unknown future. And that's particularly disturbing to me because we can move back and forth in any other coordinate. You know, up and down, left and right, forward and back, but we're stuck in time. We can't move forward or backwards in time arbitrarily. So that coordinate has a kind of a fundamental difference from the other three. Now, my professional ancestors, the earliest astronomers, basically invented timekeeping, all right? So all measures of time historically were derived from cosmic rhythms. So today we would say the rotation of the Earth, but in the day it was the movement of the sun.
Yeah.
So that gave you a day, and then the sun's position on the sky throughout the days differed, and temperatures changed, so that gave us the seasons. And then, of course, back then it was the sun doing all this, but we would learn that we rotate and we revolve around the sun. So that took really long to figure out, disturbingly long. I mean, only like 400 years ago. So what it tells you is that you can keep track of time even though you have no freaking idea what's going on. Because all that matters to you is that things repeat.
Yeah.
If you have something that repeats predictably, then you have created a timekeeping mechanism.
All physical objects, even me in my chair, exist in 3 dimensions. Everything has a width, and a height, and a length. But there is another kind of length, a length in time.
While a human may survive for 80 years, these stones will last much longer, for thousands of years. And the solar system will last for billions of years. Everything has a length in time as well as space. Traveling in time means traveling through this 4th dimension. To see what that means, let's do a bit of normal, everyday traveling just to get a feel for it. A fast car makes it a bit more fun. Drive in a straight line and you're traveling in 1 dimension. Turn right or left and you add the 2nd dimension. Drive up or down a twisty mountain road and that adds height. So that's traveling in all 3 dimensions. But how on earth do we travel in time? How do we find a path through the 4th dimension? Let's indulge in a little science fiction for a moment. Time travel movies often feature a vast, energy-hungry machine. The machine creates a path through the 4th dimension, a tunnel through time. A time traveler. A brave, perhaps foolhardy individual. Prepared for who knows what. steps into the time tunnel and emerges who knows when. The concept may be far-fetched, and the reality may be very different than this. But the idea itself is not so crazy. Physicists have been thinking about tunnels in time too, but we come at it from a different angle. We wonder if portals to the past or the future could ever be possible within the laws of nature. As it turns out, we think they are. What's more, we've even given them a name: wormholes.
We think we had wormholes figured out on paper. So Einstein's general theory of relativity, which is our understanding of how gravity works in the universe, says that any presence of mass or energy will warp the fabric of space and time. And so you can think to yourself, imagine warping space and time in such a way that you can cut a portal from your location in space and emerge in another location in space. So these wormholes, which we can describe on paper, we don't really know how to make them. And if we did know how to make them, we wouldn't know how to keep them open. Equations show that they are unstable. You might step inside and then it would collapse down on top of you, and who knows whether that's a good thing or not. It's probably not. In Interstellar, they went into black holes and through wormholes with high confidence that they would survive. But that's where the storytelling kicks in and the physics ends. I mean, it's science fiction. So a black hole is a region of space within which light doesn't come out. Nothing comes out. If you fall in, you don't come out. But it's a hole in the three-dimensional fabric of space. So it means you can fall in from any direction. Normally when we think of a hole, like you remove a manhole cover and there's a hole in the street. You fall through the hole, you come out the other side, and you can look and see where you came out. If there's a hole in space, you fall in from any direction, you end up in another place. And if that hole connects to another place, then you have a wormhole combining the two places that you might have fallen in. And you get a black hole by a very extreme high concentration of matter. And when you have that high concentration, the gravity right in the vicinity of that continues to go up and up and up. Then it reaches the threshold where light does not escape. That's when you would call it a black hole. The sun will never be a black hole, but there's stars in the night sky that we can identify that when they die and they run out of energy to hold themselves up, the thermonuclear fusion in their core ends, and the total gravity of all the material of that star overcomes everything else that would otherwise sustain it. And it collapses down to a singularity, a black hole. So you want to avoid black holes? Really? At all cost.
From the soil under our feet to the stars above, matter makes up everything in the universe. Matter comes in 4 states: solids, liquids, gas, or plasma. In solids, molecules are tightly packed and maintain their shape. Add energy, like heat, and the molecules begin to separate and melt into a shapeless liquid. More energy, and matter turns into gas. Superheated gas becomes plasma, the 4th state of matter, where electrons tear away from their atomic nucleus and float freely around it. Even in cold climates, solids like this snow turn to water when heat energy pushes the temperature above water's melting point. Liquids can't hold solid shapes, but they do have volume and move to fill the space available, even space as big as oceans. While it's obvious that ice melts, even rock solids melt when they're subjected to enough energy. Rocks melted by the heat and pressure deep in the earth erupt from volcanoes as liquid magma and lava. Gas molecules are further apart and have even more energy than liquids. Gases, like air, and hydrogen gas in the universe have no fixed shape or volume. Superheated gases in the universe are plasma. Plasma makes up more than 99% of our visible universe. Its electrically charged particles are the stuff of stars. Physicist Albert Einstein came up with an equation, E equals mc squared, to help explain the relationship between energy and mass. The simplest interpretation suggests that matter can be converted into energy and energy into matter. The theory helps explain the curious beginning of the universe when an enormous amount of energy became matter. No matter what state matter is in, it demonstrates the property of inertia. This natural law means that matter doesn't change unless it's made to by some outside force. Ice may be moved to melt, and an avalanche to slow, only when moving forces, such as heat, act on them.
Well, there is a theory, David, about what dark matter is. You talk about different universes. Let's say that our universe is a sheet of paper. We live our entire life on this sheet of paper, but directly above us, there could be a parallel universe hovering right over us, perhaps inches, centimeters away, and objects in this parallel universe would be invisible. Light travels beneath the universe, so we never see this other galaxy. But gravity goes between universes, because gravity is nothing but the bending of space. So if the space between two sheets of paper is bent slightly, gravity then moves across. So think about it. This other galaxy in another universe would be invisible, yet it would have mass. That's exactly what dark matter is. Dark matter is massive, it has gravity, but it's invisible. It has no interactions with light or the electromagnetic force. So there is a theory that says that perhaps dark matter is nothing but matter, ordinary matter in another dimension hovering right above us. We should also point out, however, that there are other theories too. Dark matter is the cutting edge of science. Some people think that maybe it's a higher vibration of the string. All the atoms of our body represent the lowest octave of a tiny rubber band vibrating all over our body. And the rubber band can have a higher octave. That next octave could be dark matter. So that's yet another explanation for what dark matter might be. So the bottom line is this. There's a shelf full of Nobel Prizes waiting for you, waiting for anyone who can come up with a convincing and experimentally verified explanation of the origin of dark matter.
Black holes, and especially supermassive black holes, are some of the most important objects in the universe. Studies have shown that especially the big ones drive the dynamics of galaxies more than just about anything else, because they're both very large, sit at the centers of galaxies like gravitational anchors, and also because they fill the galaxies full of hot radiation. They've been studied a lot, and what's interesting is there have been several in the last decade that we've discovered that are much bigger than anything ever thought possible. Several billion times the mass of the sun, formed in less than 1 billion years. We believe black holes come from stars that have collapsed. And so we know the masses of the stars they came from. And there's a speed limit at which the black hole can grow. And that speed limit precludes them being so big so fast. The mass of the black hole has a speed limit known as the Eddington limit. Stars themselves do not have the same speed limit in terms of how fast they can grow. So there was a question, could you find a place where a star might be able to grow much bigger than typical stars grow? We decided to actually take this idea, make a simulation, grow the star to the size that people think might be possible in certain configurations, and see when that star collapses to a black hole, can it actually create the types of supermassive black holes that we see in nature? What our paper shows is if you do start with this model, where you can have a special situation where a very massive star can form and then become a black hole, that we can produce the types of things that we observe in nature in many different respects. Here at Los Alamos National Laboratory, we have the unique opportunity of having the codes, the physics packages, and the supercomputer facilities needed to do this detailed calculation. And we've seen that when you throw it all together and you take all the algorithms and other things that we've developed over the years here, that we can replicate some of the more interesting things that we've seen in nature, driving the dynamics of the evolution of the universe.
Humanity's reach into the universe has now taken us to a place of myths and mysteries, the black hole. Astronomers from across the globe today announced they have captured the first ever photograph of that phenomenon. Unbelievable. CNN's Nick Payton-Walsh has more.
A grainy, almost inscrutable silhouette. It is humanity's first glimpse of the darkest and heaviest kind of entity in our universe.
We have seen what we thought was unseeable. We have seen and taken a picture of a black hole.
Simultaneously released by astronomers at press events around the globe, it's a first. Images from a galaxy 55 million light-years away. Resembling a bright halo is superheated gas circling the black hole's outer edge, the so-called event horizon. Beyond it exists a gravity force so powerful, not even light can escape, and all known physical laws begin to break down.
Black holes are major disruptors of the cosmic order on the largest scales in the universe. M87's huge black hole mass makes it really a monster, even by supermassive black hole standards. So you're basically looking at a supermassive black hole that's almost the size of our entire solar system.
The images come after years of data collection analysis by 200 scientists. With no single instrument powerful enough to capture a black hole, a network of telescopes spread across the Earth worked as one. Named the Event Horizon Telescope Project, it's the biggest experiment of its kind, and the results are scintillating astrophysicists worldwide.
You know, you feel like it's a special time. I'm sure Galileo felt he was there at a special time, right? But I think we all feel that this is a special time.
Of particular significance, the images help validate what was long thought purely theoretical.
It's a stress test for Einstein's theory of general relativity, and it has passed with flying colors. So that's what is remarkable. He was unsure that a mathematical solution would actually correspond to something real in the universe. He eventually changed his mind, but he did not believe in them because, A, he thought they could be just mathematical curiosities, and that nature wouldn't be so perverse to actually allow such objects to form.
While resolving some questions, now visible evidence of black holes creates new cosmic riddles, blazing a trail for new discoveries to come.
Mysteries abound around black holes, and we do know that there must be something more. The problem of quantum gravity remains unsolved with the current tools that we have, and black holes are one of the places to look for answers.
Nick Payton-Walsh, CNN.
Some people are even relating the black hole photo to our top story, Brexit, on Twitter, where else. Former British politician and editor of the London Evening Standard, George Osborne, showed off the paper's latest political cartoon. And another Twitter user noted the big news about the all-consuming blackness that is sucking in everything around it and destroying it. And then added, but enough about Brexit. So there you have it. Still have a sense of humor over here about the whole thing.
An accretion disk is a structure, often a circumstellar disk, formed by diffused material in orbital motion around a massive central body. The central body is typically a star. Gravity causes material in the disk to spiral inward towards the central body. Gravitational and frictional forces compress and raise the temperature of the material, causing the emission of electromagnetic radiation. The frequency range of that radiation depends on the central object's mass. Accretion disks of young stars and protostars radiate in the infrared. Those around neutron stars and black holes in the X-ray part of the spectrum. The study of oscillation modes in accretion disks is referred to as diskoseismology. Accretion disks are a ubiquitous phenomenon in astrophysics. Active galactic nuclei, protoplanetary disks, and gamma-ray bursts all involve accretion disks. These disks very often give rise to astrophysical jets coming from the vicinity of the central object. Jets are an efficient way for the star disk system to shed angular momentum without losing too much mass. The most spectacular accretion disks found in nature are those of active galactic nuclei and of quasars, which are believed to be massive black holes at the center of galaxies. As matter enters the accretion disk, it follows a trajectory called a 10x line, which describes an inward spiral. This is because particles rub and bounce against each other in a turbulent flow, causing frictional heating which radiates energy away, reducing the particle's angular momentum, allowing the particle to drift inwards, driving the inward spiral. The loss of angular momentum manifests as a reduction in velocity. At a slower velocity, the particle wants to adopt a lower orbit. As the particle falls to this lower orbit, a portion of its gravitational potential energy is converted to increased velocity and the particle gains speed. Thus, the particle has lost energy even though it is now traveling faster than before. However, it has lost angular momentum. As a particle orbits closer and closer, its velocity increases. As velocity increases, frictional heating increases as more and more of the particle's potential energy relative to the black hole is radiated away. The accretion disk of a black hole is hot enough to emit X-rays just outside the event horizon. The large luminosity of quasars is believed to be a result of gas being accreted by supermassive black holes. Lyndon Bell, 1969. Elliptical accretion disks formed. A tidal disruption of stars can be typical in galactic nuclei and quasars. Gorzadian and Ozernoy, 1979. Accretion process can convert about 10% to over 40% of the mass of an object into energy as compared to around 0.7% for nuclear fusion processes. In close binary systems, the more massive primary component evolves faster and has already become a white dwarf, a neutron star, or a black hole, when the less massive companion reaches the giant state and exceeds its Roche lobe. A gas flow then develops from the companion star to the primary. Angular momentum conservation prevents a straight flow from one star to the other, and an accretion disk forms instead. Accretion disks surrounding T-Tauri stars or Herbig stars are called protoplanetary disks, because they are thought to be the progenitors of planetary systems. The accreted gas in this case comes from the molecular cloud out of which the star has formed rather than a companion star.
Astronomers are scratching their heads after discovering a flash of light in the universe that seemed to originate from a black hole in the Milky Way. Sagittarius A was photographed emitting the mysterious flare that grew to 75 times brighter than normal levels. The event was captured by a telescope near the summit of Mount Mauna Kea in Hawaii. Joining me now is Professor of Physics at Syracuse University, Duncan Brown. Professor Brown, thank you so much for joining us. So one of the primary characteristics of a black hole is that light cannot escape it. So when we say it lit up, what does that mean exactly?
Right. No light can escape a black hole. That's why it's black. So the light that the astronomers are seeing here is actually coming from hot gas surrounding the black hole, what astronomers call an accretion disk. It's matter from stars in the vicinity of the black hole that is falling towards the black hole, spinning around the black hole, and as it spins around, it heats up and then it emits light as it gets hot. So the light is not actually coming from the black hole itself. The light is coming from the material that is surrounding the black hole. If you've ever seen the movie Interstellar, there's a beautiful picture of an accretion disk around an imagined massive black hole. That's what's being seen here. It's this matter that's flaring up in the accretion disk.
So this is a totally known and understood phenomenon. There's nothing truly mysterious about it then.
There's nothing mysterious in the sense that we haven't seen light coming from a black hole, but we still don't really understand how these accretion disks work. There's a very small amount of light coming from the black hole at the center of our galaxy. Other black holes in the universe are much brighter. We can see them across the universe. They're known as quasars. But there's not that much light coming from our black hole, and our understanding of these accretion disks is fundamental to understanding what's going on near black holes and how they work. But we don't really fully understand them yet. So this flaring is an exciting observation because it might tell us something about how these disks work.
But there's nothing about it that is essentially dangerous. Is that right?
No, the black hole is at the center of our galaxy. It's 26,000 light years away from us.
Right.
So this flaring actually happened 26,000 years ago.
That's mind-boggling to think about. Okay, so, given what we know about how fast light travels and the fact that this happened so long ago, what does that tell us? I mean, we don't even know if there's a black hole there right now in real time, correct?
Well, of course, we can't say what's going on now, but we know that these things last. Black holes of this size last a very long time. They last for billions of years. So I think it's pretty certain to say that 4 million solar mass black hole at the center of our galaxy is still there. The question is, what's happening as material goes in? Will it flare again? We've observed this accretion disk in all forms of light, from X-rays to radio waves. This flaring was observed in infrared light. And people have been training telescopes on the black hole during the summer to see if they can see any more evidence of this flaring and try and understand what's going on. So the black hole is still there. The disk itself is variable, and that variability, if we can see more of it, will teach us about what's going on near the center of our galaxy.
So you're sure the black hole is still there right now? We know that for a fact.
I'm pretty sure that black hole is still there.
So,
it will take a lot to get rid of it.
And so what does all of this tell us about how much we might not know, and what are we learning about the universe through all of this?
Well, these massive black holes, we think that most galaxies like ours harbor one of these 4 million solar mass black holes, maybe even bigger, at the center of the galaxy. And how these massive black holes are assembled, this is 4 million times the mass of our sun in a space that's about smaller than the distance between the Earth and our sun. So it's a huge amount of material packed in a small space. How do these things live? How do they grow? It tells about the history and evolution of our universe. And you just showed the beautiful picture of a black hole imaged in a distant galaxy by the Event Horizon Telescope. That's seeing the shadow of the black hole against this glowing material that's falling in. It teaches about the nature of gravity. It teaches us, was Einstein right about general relativity and how gravity works? And it teaches us how our universe evolves and grows and where we came from and where we're going.
I didn't think the jury was still out on Einstein's theory of relativity. Hasn't that been proven, or are there still instances where we're not sure whether that is the running theory?
It's been proven pretty well. Observations of merging black holes in gravitational waves have pretty much cemented Einstein's theory as the premier theory of gravity. But there's still some room when we get into really extreme situations that we might see some deviations that might hint about some new physics that we don't know.
Right.
And we don't know how to marry relativity with quantum theory. So we know that relativity is not the ultimate theory of the universe. There's more for us there to learn.
Oh, there's room for another Einstein and another theory. So I'm just curious, though, you said that we don't quite know why this happens. We don't quite know why these gases react this way around the black hole. Are there some theories behind it?
Yes, there could be some theories about why this flaring happened. There could be some material from a star. There's a star called SO2 that passed pretty close to the black hole recently. So perhaps some material was torn off that star and fell into the black hole and caused some flaring. There's been some giant clouds of dusty material that passed near the center of our galaxy that there's evidence that maybe they interacted with the black hole. So maybe this is some material that's been pulled off and fallen into the black hole, causing some flaring. Maybe it's just a clump of material in the disk. I mean, what this tells us, our knowledge of what's going on there isn't complete, and we need more observations to understand what's going on.
All right. Fascinating stuff. Professor Duncan Brown, thank you so much for joining us.
Thank you.
Scientists can't directly observe black holes with telescopes that detect X-rays, light or other forms of electromagnetic radiation. However, we can infer the presence of black holes and study them by detecting their effect on other matter nearby. For example, if a black hole passes through a cloud of interstellar matter, it will draw matter inward in a process known as accretion. Over the years, researchers have found out a lot about black holes. They are not an empty space, but rather a great amount of matter packed into a very small area. It's like having the sun's mass squeezed into a small city. The result is a gravitational field so strong that nothing, not even light, can escape. In recent years, NASA instruments have painted a new picture of these strange objects that are to many the most fascinating objects in space. Recently, scientists have discovered a black hole that is spinning at one of the highest speeds ever recorded. A black hole was spotted by Astronaut, India's first astronomy satellite, in 2016. The black hole in question can be seen in the star system 4U163047. The hole was also noticed by NASA primarily due to the bursting out of X-rays. The researchers said the gas and dust finding its way into the black holes were causing the bursting out of X-rays that NASA and Astronaut observed. After observing its effects, it was announced the black hole has the size of roughly 10 times that of the Sun. This means it has a diameter of over 8,649,000 miles, or 13,919,216 kilometers. The X-rays also told the scientists and researchers that the black hole is spinning at a very rapid pace. NASA has gone forward and said that this black hole is spinning at a rate close to the maximum speed allowed that was determined by Albert Einstein in his theory of relativity. In other words, the black hole is spinning almost as fast as the speed of light. This observation is according to Rodrigo Neiman, who is the lead researcher for the study of this black hole. Measuring a black hole can either be done by the mass of the black hole or its spin rate. Spin rate ratios are between 0 and 1. This black hole is spinning at a rate of 0.9. This rate has been confirmed by Astrosat as well as NASA. It was also recently announced by scientists in Japan that they have discovered what they believe is a new type of black hole at the heart of the Milky Way galaxy. This giant black hole, which is believed to be 100,000 times the mass of the Sun, was discovered hidden within a giant cloud of molecular gas, and is the best evidence found of intermediate mass black holes. What's incredible is this has never been officially identified before. Thanks for watching, and don't forget to subscribe for more videos.
We are all aware of the formula speed multiplied by time is equal to distance. This gives us the distance. If we want to find the speed, we transpose time to the other side. And if we want to find the time, we transpose speed to the other side. A good way to remember this is by remembering this triangle with a T. We have speed and time at the bottom and distance on top. If we want to find the time, it will be d over s. If speed, it will be d over t. If we want the distance, it will be s times t. Really simple, isn't it? How are these parameters given to us? Speed is given as a rate, something like 10 kilometers per hour. Say we travel at this rate for 2 hours. What will be the distance that is covered? It will be 10 times 2 or 20 kilometers. Observe that the units are also working out perfectly. Kilometers over hours multiplied by hours. Hours get cancelled and what remains is kilometers. With this formula, if we are given any two parameters, we can easily find the third. Units of time and distance are straightforward. But units of speed can get interesting. It can be provided to us as kilometers per hour or sometimes even meters per second. And it is important to keep in mind that the units of all three parameters must be in sync. It would be incorrect to say 10 meters per second multiplied by 2 hours is 20. But 10 meters per second times 2 seconds will equal 20 meters. That's because seconds get cancelled. So sometimes we may need to convert the speed from kilometers per hour to meters per second or vice versa. Let's say we have been given the speed in kilometers per hour. How would you convert it to meters per second? Pause the video and think about it. How would you convert kilometers per hour to meters per second? If we multiply the value in kilometers per hour with 5 over 18, we will get the answer in meters per second. Yes, that's how easy it is. Let's see why. We know that 1 kilometer is 1000 meters. And how many seconds is 1 hour equal to? 1 hour is 60 minutes and 1 minute is 60 seconds. 60 times 60 will be 3600 seconds. Now we simply reduce this fraction to its simplest form. We cancel the 2 zeros. 2 times 5 is 10 and 2 times 18 is 36. So this is equivalent to 5 over 18 meters per second. Yes, 1 kilometer per hour is the same as 5 over 18 meters per second. In time, speed and distance problems, we need to keep the units in mind. So based on what we learnt, why don't you try converting 54 kilometers per hour to meters per second? As 1 kilometer per hour is the same as 5 over 18 meters per second, we multiply this with 5 over 18 to get the answer in meters per second. 18 times 3 is 54 and 3 times 5 is 15. 54 kilometers per hour is equal to 15 meters per second. And it goes without saying that to convert from meters per second to kilometers per hour, we have to multiply by 18 over 5. This topic is best understood with examples. We will cover more than 20 different types of examples in the coming sessions.
We all move along a straight timeline. That's the way in which the universe evolves. But it is possible to affect that flow. You got it. In Einstein's theory, time can be affected by speed. That is to say that the faster you move, the more time slows down. As early as 1971, an experiment was done. What they had was 2 atomic clocks. One of the atomic clocks was kept stationary at the Naval Observatory. The other atomic clock was put on an ordinary passenger jet and flown around the world at the speed of sound. When they brought the passenger jet back and they compared the clock on the passenger jet with the clock that had been stationary at the Naval Observatory, they found the clock on the passenger jet had actually slowed down. This meant that that plane had actually traveled fractions of a second into the future. Now, this one didn't seem that dramatic, but when we have rockets that can go close to the speed of light, this effect will not just be in terms of fractions of a second, it will be in terms of years. In other words, a space traveler going out in space and traveling close to the speed of light, she may be out there for only 5 years, but when she comes back, she could come back and find out that she's younger than her children. So, in a nutshell, Einstein's special theory of relativity is about how time is affected by speed. But he had another theory. That theory says that time slows down due to gravity, which means that a clock here at the surface of the Earth actually runs slower than a clock at a higher altitude. About 12,000 miles above us, there are 24 satellites in geosynchronous orbit covering different parts of the Earth. And the way in which the system works is that that satellite is sending a signal at a certain time that reaches your GPS unit at a certain time. We know the time that the satellite sent the signal, and we know the time that you received the signal in your unit. Okay? We also know the speed of the signal. It's the speed of light. It turns out that when you know time and you know speed, you can calculate distance. So that's how the GPS system works. However, engineers found that the system wasn't working properly initially. And the reason is they forgot about Einstein's theory of gravity, his general theory of relativity. And when they consulted with the physicists about that, what they realized was that the time, the clock in your unit, is actually running slower than the clocks on board the satellites. It shows that gravity does affect time. This was something that really caught my imagination because of the work of a rather eccentric mathematician by the name of Kurt Gödel. Gödel actually showed that if we were living in a rotating universe, this universe could create loops in time. And by loops in time, I mean you actually have a timeline that's normally in a straight line going from the past, present, and future is turned into a loop. And you could actually go along that loop in time and you could go back into the past. And he based his work squarely on Einstein's general theory of relativity. That, to me, was another epiphany because I said, good heavens, that's what I want to do. The special theory of relativity allows you to go into the future, but the general theory of relativity allows you to go back into the past. And I thought, that's what I have to study, is the general theory of relativity. It took years, years, but ultimately I was able to understand Einstein's general theory of relativity. But that's because I had the passion. I knew that the general theory of relativity was going to open up the doorway to the past for me.
If you ever find yourself in a tour of some of the most fantastic places in the galaxy, make sure you stop by the center. It's a pretty exciting place. Mainly that's because of the supermassive black hole, more than 4.3 million times the mass of our sun, that's sitting in the middle of the Milky Way. Black holes are what's left over when a star collapses, and they have an incredibly strong gravitational pull. Because of that super powerful force, the supermassive black hole's neighborhood is the hottest, densest, and most turbulent place in the galaxy, stretching nearly 1,000 light years across. Over time, it's drawn in about 80% of all of the dense molecular hydrogen gas in our galaxy, the stuff that makes stars, which is why it's called the central molecular zone. But combine the gas clouds with the supermassive black hole's gravitational pull, and you get some weird effects. Not only is the region full of dark clouds, it's also scattered with superstar clusters and the corpses of dead stars. Much of the gas in the molecular zone is clumped up, lying along a twisted ring of dusty gas clouds around 326 light years from the central black hole. These gas clouds orbit the center of the Milky Way at almost 300,000 kilometers an hour, following the same orbit like beads on a string. But the ring is a little off-center, so at one point the clouds end up within just 200 light years of the black hole. And that's when things really start to get weird. The gravitational pull compresses the clouds even more, and one of them is so dense that it's nicknamed the brick. At an average density of 10,000 atoms per cubic centimeter, the brick would be considered a high vacuum here on Earth. But out in space, it's more than 10 times the density where star formation would normally begin, and astronomers wanted to know why. In 2012, a group of researchers got the first glimpse inside the brick using a set of telescopes called the Atacama Large Millimeter Array, and in the process, they might have found the answer to why it hasn't started making stars yet. They discovered that the gas is made of both filaments and dusty clumps, and it's preparing to form star clusters with hundreds of high luminosity or super bright, high-mass stars. But the high-energy environment moves the gas around so much that the lights haven't turned on quite yet. Eventually, the brick will reach just the right conditions where it can make stars, and it'll quickly form a lot of really big, really bright ones. Then it'll become a lot like another cloud in the molecular zone, called Sagittarius B2, which is a huge cloud, almost 10 times as massive as the brick, and the most active site of star formation in the entire galaxy. It probably went through the whole black hole squeezing process at some point, and within the last few tens of thousands of years, it burst to life with dozens of extreme high-mass stars. And in the hottest spot in Sagittarius B2, there's a young star cluster that produces more than 10 million times the luminosity of our sun. These hot stars pour out so much heat and energy that all sorts of complex chemical reactions can happen in the surrounding clouds. So that's where we tend to find complex organic molecules like formaldehyde, different kinds of alcohols, and ethyl formate, a molecule that smells like rum and tastes like raspberries. But Sagittarius B2 won't stick around forever. At some point, the fierce winds and radiation from the hot stars will blow the cloud apart, leaving behind enormous superstar clusters. There are a few of these formed within the last few million years, already in the molecular zone. Two of the most famous clusters are called arches and quintuplet, and they pack stars in densities more than 100,000 times higher than in our part of the galaxy. The quintuplet cluster contains one of the most luminous stars known, the pistol star. And it probably couldn't have formed anywhere else in the galaxy because it would have needed a lot of mass to pile up really quickly. Overall, every few million years, the central molecular zone turns so much gas into stars that it uses up 100,000 times our sun's mass. But any losses are quickly replaced by gas flowing in from farther out in the galaxy, so the star formation has continued for millions, if not billions of years. With such a long history of forming heavy, bright stars, the molecular zone has another group of residents that you won't find anywhere else in the galaxy. Lots and lots of dead stars. High-mass stars burn through their fuel really quickly, and they'll go supernova in as little as 3.5 million years after they first form. Compare that to our sun's 10 billion years. After they explode, they leave behind stellar corpses in the form of small black holes and neutron stars, tiny, high-density cores. Over the more than 10 billion year lifespan of the galaxy, generations of stars have formed and died in the molecular zone. So in addition to being the galaxy's busiest stellar nursery, it's also the largest and most crowded graveyard. Thanks for watching this episode of SciShow Space, and thanks especially to our patrons on Patreon who help make this show possible. If you want to help us keep making episodes like this, just go to patreon.com/scishow to learn more. And don't forget to go to youtube.com/scishowspace and subscribe.